Hi there, folks. Today we're looking at properties of parallelograms. So parallelograms themselves, we already know what those are. Those are quadrilaterals where the opposite sides are parallel. And really, that's all we know based on the definition. But now we want to come up with some ideas about what other properties those opposite sides have, or what properties do the opposite angles have, the consecutive angles, that kind of thing. Okay. And so when we talk about opposite sides, we're talking about sides that are not touching one another. So like BC and AD would be examples of opposite sides, AB and DC. Opposite angles are angles that are on opposite sides, which again, as we're kind of counting the angles going around the outside, A, B, C, D, as I list those are consecutive angles. So A and B are consecutive, B and C are consecutive, C and D, D and A. All right. But opposite means that they're non-consecutive. So something like B and D would be opposite angles. Okay, they don't share any of their pieces in terms of creating those angles. Okay, and so just be aware of those terms. Opposite sides. That should be fairly obvious. The opposite angles thing should be fairly obvious. Students usually trip over the consecutive angles. Just as we're listing these going around the outside, A follows B, so those are consecutive. B and then C, C and then D, D and then A. Okay. So the first thing we're going to look at is, given that I have a parallelogram here, I want to prove that AB is congruent to CD. I want to prove that AD is congruent to BC. So I essentially want to prove that the opposite sides are congruent. So taking my statements and my reasons here, again, I'm going to start with what I know, and I know that this thing is a parallelogram. That's really all that's given to me. But as I kind of think about what that means that the opposite sides are parallel, so I could right away say that AB is parallel to CD, and BC is parallel to AD. Okay, and that's just the definition of parallelograms. That's what a parallelogram is. But now from here, there's not really much else that this gives me, okay? And so from here, I'm going to have to add a little something to this. I'm actually going to draw a diagonal across this thing. So I'm going to draw a diagonal from A to C. I could draw the diagonal from B to D. That would be fine as well. All right. Either of the one of those would be okay. But what this ends up giving me is really two triangles. And I know a lot of stuff about triangles. So this is going to be helpful in terms of getting proofs where things are congruent to one another, because I know how to prove the triangles are congruent. Okay. And so as I start to think about those triangles, and I start to think about, something like these guys being parallel. Well, AC, the thing that I've just drawn, that's a transversal. And if that's a transversal, I know things about the angles. Like, for example, I know that angle 1 here and angle 2, I'll label them that way. I know that those are congruent because those are alternate interior angles. Okay. Likewise, if I look at the other pair, if I look at AB and CD, all right, those being parallel, I right away know stuff about those angles as I start to think about, like, angle 3 here and angle 4 would be congruent because those are alternate interior angles, okay? And so as I kind of look at these things from the perspective of parallel lines with a transversal, I easily have a bunch of angles that I can say are congruent. And so that's what I'm going to do in my next step. I'm going to say that angle 1 is congruent to angle 2, but also I'm going to say that angle 3 is congruent to angle 4. And I can say that it's the same reason, it's the same justification here. Alternate interior angles are congruent. But it's looking at different parallel lines, okay? The one set is looking at BC and AD for those congruent angles. The other set is looking at the parallel lines of CD and AB. They're just each using that AC as a transversal, okay? And then, so what I have here is I have two angles. The other thing that I have is that AC is congruent to itself, okay? Because it's the same thing. So I can easily say that AC is congruent to AC. And again, that's because of the reflexive property. Okay. And now from here, I can say that those two triangles are congruent. If I look at the two triangles that are given here, I've got triangle ABC. And I can say the triangle ABC is congruent to triangle, let's see, CDA. And again, that's because of angle, side, angle. Okay? And now from here, if I have the two triangles congruent, I can say anything I want to about the corresponding pieces of those triangles. Okay? And so as I look at this thing, AB and CD match up within these two congruent triangles. So that means that I could say that AB is congruent to CD. And I could say something like AD is congruent to BC. And that's because of CPCTC. Okay? If the triangles are congruent, then their parts are congruent. All right? And that's it. So what I've just shown is I've shown that if I have a parallelogram, just knowing that this thing's a parallelogram, yeah, I added a few things here, but knowing that it's a parallelogram, I can immediately then show that the opposite sides are congruent. Okay? And so that's the first theorem we have listed here. If a quadrilateral is a parallelogram, then the opposite sides are congruent. Okay? And so that's one of the properties we have. It's not the definition. The definition only gives us that the opposite sides are parallel. But the properties, what we can do with that is show that the opposite sides are congruent. Okay? So now that we've proven this, we can use this as often as we want. We can just say, hey, if it's a parallelogram, opposite sides are congruent. Likewise, if it's a quadrilateral, if the quadrilateral is a parallelogram, then the opposite angles are congruent. That's the same proof, and I'm not going to redo that one. But if you kind of look at this guy right here, if I were to change this last step, and instead of doing those sides congruent, couldn't I say something like angle B and angle D are congruent because of CPCTC? And the answer is yes. Well, that would show me that those opposite angles are congruent. And then if I wanted to get A and C, I would have just had to draw the other, would have to have drawn the other diagonal. Okay, if I had drawn the diagonal from B to D and done the same proof, I could get A and C congruent by CPCTC as well. Okay, and so this second theorem here is really would be proven the same way. Okay, so if it's a parallelogram, the opposite angles are congruent. And then the last one here, if it's a parallelogram, the consecutive angles are supplementary. That one is like a two-step proof. As we kind of look back up, if I were to look back up at like this original guy, if BC and AD are parallel, let me kind of extend these guys a little bit. Look at like AB as the transversal. Well, think about what kind of angles this one and this one are. Think about what kind of angles those are. Those are same side interior angles. And we already know that same side interior angles are supplementary. Well, that means that consecutive angles on this parallelogram are supplementary, okay? Because each of them become same side interior angles of parallel lines, okay? And so really you could almost list that almost like a corollary because it relates so directly to same side interior angles, okay? So here's what we have in terms of properties so far. Opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, okay? If I look at this guy, using what I know in terms of the properties, since this thing's a parallelogram, I can see the opposite sides are parallel. Right away, one of the properties I have is that opposite sides are congruent. So I'm going to say that, hey, the 2y plus 15 must equal the 4y minus 7. Okay, because those are opposite sides, they have to be congruent. And I can solve. I'm going to subtract the 2y from each side. I'm going to add that 7. And I'm going to divide by the 2. So I end up with y equals 11. And of course, you can always plug that thing back in and check it to make sure. And then if I look at the angles that are labeled, B and D, those are opposite angles. And the thing I know about opposite angles is that they are congruent. So I can say that the 4x plus 1 equals the 125. And I solve, I subtract that 1 from each side. And then I divide by the 4. And I end up with a 31. Okay? If I look at the next one, same kind of thing. I just have to look at this and say, okay, it's a parallelogram. What's labeled here? When I look at AB and CD, those are opposite sides, so I can set those equal to one another because opposite sides are congruent. And this one, because there's an x squared, this is a quadratic. Remember, quadratics, we want to get 0 on one side, so I'm going to subtract the x and the 6. And then you have to solve this by factoring, completing the square of the quadratic formula. Always try factoring first, build a bridge. Back to our algebra skills here. Two numbers that multiply to a -6 but add to a -1 are a -3 and a +2. Because the a value, the number in front of the x squared, is a 1, I can go right to the two factors of x minus 3 and x plus 2. And then I can set each of these equal to 0. So here I add the 3, here I subtract the 2. And students a lot of times will toss one of these answers automatically. They'll toss the negative because they're saying, oh, well, we can't have a negative value. Well, we can't have a negative side length, but plug it in. Like if I were to plug the -2 in, here I get a 4, and here I get a 4. Well, isn't that acceptable? Could each of those sides be a 4? So yeah, x can equal a negative, but it can't give me a negative side length. So yes, be a little bit skeptical when you see that negative, but make sure you plug it in. That's an acceptable answer because the side length is still positive. If you plug it in and it gives you a negative side length, well, then it's no good, okay? And you can check the other one too. It would give you a 9 and a 9. That would also be acceptable. So there's really two options here based on the values that we're given, okay? And so, yes, either one of these is acceptable. It's okay for x to be negative, but if it gives me a negative side length, that's no good, okay? And then when I look at the angles, angle A and angle D, those are consecutive angles, which means they're supplementary, which means the 2y minus 5 plus the 35 has to equal 180 degrees, okay? So they're supplementary. I'm going to combine like terms. Sorry, that's a plus sign. And I subtract the 30. Sorry, I got a little ahead of myself. Now I subtract the 30. There we go. There's the 150. And divide by the 2. Okay. If I look at this guy, I'm going to use what I know. I'm going to use the properties of parallelograms to construct a proof here. So given that ABDF is a parallelogram, AC is congruent to EC, I want to prove that angle BDF is congruent to angle DEF. And one of the first things I'm going to do, just to make life a little bit easier for myself, I'm going to label BDF as angle 1, and I'm going to label DEF as angle 2. Okay, just to make this a little bit easier so I can write angle 1 and angle 2 instead of these things. That's what I'm trying to prove. Okay, and now they're labeled a little bit easier, and I'll label some other angles probably using some numbers as I go. Okay, and so I want to think about what I know. So right away, I know that this thing right here is a parallelogram. Okay, and I want to think about the kind of things that gives me. All right, I would know that BD is congruent to AF and AB is congruent to DF. All right, that might not necessarily help me because I'm trying to talk about angles here. So maybe I would want to say that like angle B is congruent to angle F, or angle D is congruent to angle A. All right, so I want to think about those things. The other piece of information that gives me here is that AC is congruent to EC. Okay, and so when I kind of zoom out and kind of think about this thing as a whole, AC, that's like this guy, is congruent to CE, that's like this guy. Well, that's kind of looking at this big triangle as a whole. And so if those two sides are congruent, I'm talking about an isosceles triangle. Well, I want to relate this to angles. The whole proof is talking about angles. So think about what we know about the angles of an isosceles triangle. Well, you know, the base angles are congruent, so A and E would be congruent. And so hopefully as I've kind of talked about those pieces, you can start to construct this proof. So here we go. Now that I've kind of just talked it out, let's go to our statements and reasons. I have everything I need in the couple statements that I've made leading up to this. So let's start with what's given. That this is a parallelogram. And that was given. And now from here, there's a couple of things I could say. I could say that, hey, if that's a parallelogram, I know that opposite angles are congruent. And so I'm going to label this, I'm going to call this angle 3 down here. That's one of the ones I talked about, 1 and 3 being congruent. And that one I could have left because it's, you know, angle A. That one is acceptable to be labeled as angle A, but that's okay. So let's see, I'm going to say that angle 1 is congruent to angle 3. And that's because our properties of parallelograms, I know if I have a parallelogram, the opposite sides are congruent. Okay, so opposite sides, that's a terrible looking congruent symbol. I'm going to do better. So opposite sides of parallelograms are congruent. And then the other thing I know based on the given is that because AC is congruent to EC, all right, because it's an isosceles triangle, I know that those base angles are congruent. So I could immediately say that angle 3 is congruent to angle 2. And you could say that, because, you could make the justification that, if two sides of a triangle are congruent, the sides opposite those are congruent. I'm just going to label it this way and say, hey, base angles of isosceles triangles are congruent. Okay. And yeah, maybe I should have a step in there that labels triangle ACE as an isosceles triangle because it's, meets the definition. All right. But again, reasonable justification. All right. We'll be okay there. And now from here, if I just look at what it's given, I have 1 is congruent to 3, 3 is congruent to 2. Well, right away, I can then say that 1 is congruent to 2. So angle 1 is congruent to angle 2. And that's just my transitive property. Okay, 1 to 3, 3 to 2, so 1 to 2. And that's it. Those are the two angles I was looking for. Granted, they were labeled as BDF originally. And, if someone's being really picky, you would have to have a step in there where it says, I'm going to substitute a BDF for angle 1. I'm going to label it differently. And then at the end, you'd have to rewrite it again. I'm just going to leave it like this. Okay. All right, one more theorem for these things. So one more property that we're going to look at in terms of parallelogram. So we already have stuff with the parallelogram itself in terms of the opposite sides and opposite angles and consecutive angles. But now I want to talk about the diagonals of a parallelogram, okay? And so for this one, I want to prove that AC and BD bisect each other. So AC and BD are the diagonals. I want to prove those bisect one another. So in other words, I want to show that AE is the same as EC. Okay, I want to show that BE is the same as ED. I want to show that E is the midpoint of each of those. Okay, and so as we kind of look at this thing, I have 4 triangles that were formed by drawing those diagonals. And so right away, I'm thinking, okay, I want to go the route of looking at the triangles here because that's, one of the things we know a lot about in terms of proofs. Okay, so we want to start looking at those triangles. And really, I'm only going to need to show that 2 sets of these are triangles are congruent. I'm not going to have to go the route of showing all 4. Okay, and so as I look at this thing, let's start with what's given. Oh my goodness, I drew a triangle instead of a parallelogram. Let me try again. So all I'm given is that this thing is a parallelogram. Okay? And so if I know it's a parallelogram, right away I can say that the opposite sides are parallel. And I'll label the other ones too. Not that I'll necessarily need that. I don't know exactly what I need until I kind of start working through this thing. But again, that's the definition of a parallelogram. Okay, so now that I have those opposite sides parallel, let's start thinking about those triangles and what else I know maybe in terms of the parallelogram. So right away, if I know those are parallel, I can say things like, maybe I'd label this angle right here. So this angle right here, well, that would be the same as this angle right here. So I'm going to call them angle 1 and angle 2 because those are alternate interior angles, okay? And that came right from those things being parallel, right from that definition. So using BD as a transversal, right away, I can say that angle 1 is congruent to angle 2, okay? And that's because those are, again, same side interior angles. Again, those are only congruent when I have parallel lines. So same side interior angles of parallel lines are congruent. The other thing I have here, kind of breaking away from the definition, is just knowing that this is a parallelogram using my properties. I could say that BC is congruent to AD. Okay, I can say those are congruent because they're opposite sides of the parallelogram. Okay, and that's one of the properties we were just talking about. Again, that's a property. Opposite sides, parallelogram are congruent. Okay. And so as I start to look at this, I'm looking at really those two triangles, triangle BEC and triangle AED. As I look at those triangles, I have 2 out of the 3 pieces I need to show that they're congruent. I have a side, I have an angle. Really, all I need is one more angle, or somehow get the side. I'm not going to be able to get the side, but I can get an angle. Okay. And so as I look at this thing, look at these angles in the middle right here. That's going to be the key. As we look at those angles in the middle on this thing, all right, I could easily look at this and say, hey, wait a minute. This angle right here, angle 3 and angle 4, this is a really easy route to go. So those are vertical angles, so I know that angle 3 and angle 4 are congruent. Okay. And so if I know that those are congruent, now look at what I have. I have angle, angle, side for each one. Okay. As I kind of work my way around in that top triangle, it's 3, 1, side. Okay. And in the bottom one, it's 4, 2, side. And so I know that these two triangles now are congruent. I'm going to label the top one as EBC, kind of following that angle trend. And underneath, I can say that that's congruent to triangle EDA. And again, I'm just labeling that in the same order that it would be angle, angle, side, because it's a nice way to kind of keep it in the proper labeling fashion here. And so as I look at this thing, those are congruent because of angle, angle, side. And now from here, I can use CPCTC to show that the different pieces are congruent. So I could say that something like, AE is congruent to EC because those are corresponding parts. I could also say that BE and ED are congruent. And again, that's because they're corresponding parts. And so I can say all that because of CPCTC. Okay, corresponding parts of congruent triangles are congruent. Well, if I know that AE, if I come back up here and kind of label this, if I know that this guy's congruent to this guy, and this guy's congruent to this guy, well, that's the definition of bisectors, is that it, splits this thing into 2 congruent pieces. So I pretty much have my proof here. I just have to say it. That AC and BD bisect each other. And I can say that, I can justify that because I literally have the definition, okay? That's it. And so again, to kind of recap what we've done here, here's the theorem. If a quadrilateral is a parallelogram, the diagonals bisect each other. They cut each other in half, all right? They kind of form a midpoint for each diagonal as they cross one another, okay? And so if I use that here, it says find the value of x and y. So for this one, I would say, hey, this thing cuts each other in half, so that means that this piece and this piece are congruent, all right? It also means that this piece and this piece are congruent, okay, because they bisect one another. So I really have 2 equations I could set up here. One of them is that x equals y plus 2. The other one is that y plus 10 equals the 2x minus 8. And this is a system of equations. I can solve this system by substitution because this guy's already equal to x. X is by itself, so I'm going to plug that in for x. And now from here, I'm going to solve. I distribute. I combine like terms. I'm going to subtract that y from each side. And I'm going to add the 4. So I get y equals 14. I come back over here, plug it back in. Turns out that x equals 16. Okay? And that's it. Okay, so properties of parallelograms. Yes, the definition of a parallelogram is the opposite sides are parallel, but it automatically gives us that the opposite sides are congruent, the opposite angles are congruent, consecutive angles are supplementary, and that the diagonals bisect one another. Okay?